Okay, so in this video I'm going to have a look at the 2023 Higher Level Maths Leaving Cert Paper 1, question 5. So let's see, in part A here we have a function and it's 1 over 5x squared plus 7. Find f prime x, the derivative of x, give your answer in its simplest form. Okay, so again, a couple of ways of doing this. You can use the chain rule, which is probably easiest. So if we have f of x is equal to 1 over 5x squared plus 7 can just be written as 5x squared plus 7 to the power of minus 1. So if we write f prime x, if we find the derivative, then bring the minus 1 down, write out what's in the bracket, reduce the power by 1, so that's going to be minus 2, and then multiply by the derivative of what's in the bracket. So that's just going to be 10x. So if we simplify that, it's minus the 10x will remain on top. And on the bottom we've got 5x squared plus 7, which is squared. That's it really. You can do this using the quotient rule as well, so I might just do it that way as well. So just write our function out. It's f of x is equal to 1 over 5x squared plus 7. So if you take u as being the numerator, v as being the denominator, we've got f prime x then is going to be equal to v, which is 5x squared plus 7, times du dx, so we've got to differentiate the numerator here, that'll just give us 0, minus u, which is 1, and then we've got to differentiate the denominator here, so that's just 10x. That's all over v squared. So v is 5x squared plus 7, which we have to square. That'll give us, well, this will just become 0, and here we'll end up with minus 10x on the top, and 5x squared plus 7 squared on the bottom. And it says give your answer in its simplest form, and I don't think we can do anything more with that. Nope, I think that's about it. Okay, so that's it for part A. Let's have a look at B. So B here, okay, we got this kind of complicated looking function here, g of x, and we've got to find the derivative of it and then put in pi over 2. So the procedure is straightforward, but it might get a little bit complicated here because of the fact that we have tan of a fraction and we have log. But let's see how we just run through the procedure anyway. So we have g of x, we want g prime x. So let's start. It's a product, so we're going to use the product rule. So this here is going to be u, and this here, the log of x, is going to be v. So let's run through that then. So it's u dv dx plus v du dx. Again, it's that formula's in your tables. So u is tan x over 2. So that's u. And then we want to do dv dx. So log x is going to become 1 over x plus v, which is log x. Again, brackets are very important here. Log of x, and then we want to do du dx. So it's u dv dx plus v du dx. So we want to find the derivative of tan of x over 2, or tan of a half x. So we have tan half x. So to do this we would use the chain rule. So if you look up, again in your tables, you'll find that if you differentiate tan x, you'll get sec squared x. So we're going to get sec squared x over 2. But because it's not tan of x, it's tan of some function of x, we've got to use the chain rule here. So it's not only sec squared x over 2 or half x, we've got to differentiate half x as well, so we've got to multiply by a half. If you differentiate half x, you get a half. So this is it, okay? Now let's just try and tidy this up a little bit. Let's see, I'll put that 1 over x first, and then I've got tan x over 2. Now here I've got log x, and then I've got sec squared x. Now there's a couple of ways of translating or transforming that sec squared x over 2. From your tables you can see that sec squared a is equal to 1 plus tan squared a, so we could use that. Or what I'm going to use is the sec of a is 1 over cos of a, so the sec squared a is 1 over cos squared a. So really this just becomes 1 over cos squared x over 2. So sec of x is 1 over cos of x. So sec squared x over 2 is 1 over cos squared x over 2, and then we're multiplying this by a half. Okay, so at this stage I think what I'll do is I'll leave it like that and put in the pi over 2 at this stage instead of x. So what we want is g prime pi over 2, or 90 degrees there if you like. So let's do all of this. Now we're going to end up here with 1 over pi over 2. So wherever you've got an x here, you're putting in pi over 2, in other words. So you've got tan pi over 2 over 2. You've got log pi over 2. And then you've got 1 over cos squared pi over 2 over 2. And out here we've got a half. Okay, so it looks complicated, but it's not really. It should simplify fairly nicely, I think. So let's see what happens. Let's see, here we've got 1 over a fraction, so just flip that fraction upside down, so it's 2 over pi. This here becomes tan, I'll write it out, tan of pi over 4, or tan of 45 degrees, which is always handy. So pi over 2 divided by 2, or in other words, half of pi over 2 is pi over 4. Here we've got log pi over 2. And here we've got 1 over the cos squared of pi over 2 divided by 2, that's pi over 4. And out here we have a half. Okay, so next line then, we've got 2 over pi times, now tan of pi over 4. The tan of 45 degrees is just 1. So there's just a 1 here if you like. Log pi over 2. Now out here, this should simplify, I think. Let's see, we've got cos squared pi over 4. Well, the cos of pi over 4, the cos of 45 degrees is 1 over the square root of 2. And we've got to square it. And then out here we've got a half. Okay, so let's see, here we have 2 over pi plus the log of pi over 2. Now, what's going to happen here is you've got, let's say, 1 on the top here, and down here you've got to square this fraction. Well, if you square 1, you get 1. If you square the square root of 2, you get 2. And here you've got a half. You can probably see what's going to happen here. But anyway, we've got 2 over pi plus log pi over 2. And then all of that is multiplied. I should have a big bracket here, really. And here I'm just going to end up with 2. If you have 1 divided by a fraction, we're going to flip this fraction upside down and multiply. So that just becomes 2. We've got to multiply that 2 by a half. So finally then we get there. Let's see, we've got 2 over pi plus log pi over 2, and then half of 2 is 1, so we just have a 1 out here, which I won't write in. That's really it. I mean, I've probably done a few more lines than I probably should have done there. Maybe you would have done it a little bit quicker, but I've just done each line fairly pedantically there. Let's see, what way did they want the answer here? They wanted it looking like this. Give your answer in the form a plus log b, where a and b are real. A plus log b. So this is our a here. Is that real? Yes, it is. Plus log b. This is our b here. Is that real? Yes, it is. So really that's it. That's where I'm going to finish here. Okay, so that was kind of long-winded, but as I say, you guys might have done it a little bit quicker. Okay, let's have a look here. We have a diagram. Again, this looks a little bit complicated. It's not really, I think. Let's have a look and see what they're asking. The diagram below shows 3 sets. So you've got set A here, you've got set B here, and you've got set C here. And the function f, so this is the function f here, mapping A onto B, and this is the function g here, which maps B onto C. And they tell us that there, okay. So the cardinal number of A, that's the number of elements of A in A, is the same as the number of elements in C, the cardinal number of C, which is 4. So you can see 1, 2, 3, 4, 1, 2, 3, 4. The cardinal number of B, the number of elements in B, is 3, and you can see that you've got an airplane, you've got whatever that is, it looks like the Earth, I think, and then down here you've got a cloud. So you've got 3 things here. Find the value of g of f of 3. Okay, so this is fairly straightforward. I mean, this is just composite functions. You've got to do f first, and then whatever you get when you do f, you stick that into g and see what happens. So let's do f of 3 first. If we look at 3 from f here, what happens? It's mapped onto this thing here, this world thing here, this Earth. And what happens then when you put that into g? Well, it's mapped onto w. So it's fairly straightforward. Our answer is just w, and that's it. Okay, so that's part C. Let's have a look at part 2 of C. We've got explain why g, which maps B onto C, is injective but not surjective. Okay, so we are going from B to C here. Okay, B to C. So let's have a look. Why is it injective? Well, it's injective because every output that we have here is an image of a unique input. So this is the image of only one input here. This one here is the image of only one input. This image here is the image of only one input. You can have, for example, something like this with an arrow going that way. This now would not be injective because this image here is the image of 2 inputs. But in our case, each of our outputs here is the image of only one input, a unique input. So that's what I need to write down. It's very easy to get the words mixed up in this particular question, but let's write it out anyway. So B mapping onto C is injective because each output is the image of a unique input. And that's it. They really just want to know, do you understand what injective and surjective mean? So let's have a look. So it is injective, but why is it not surjective? It's not surjective because we're not using all of the elements in the codomain. We're not using all of these elements here. We're not using y. We're using x, we're using w, we're using z. They're all outputs, but y is not one of the outputs. It's a member of the codomain, but it's not one of the outputs. So that's really it. So G again, from B to C, is not surjective, since every element in the codomain, C is not an output. So Y is not an output. And that's really it. So it is injective because each output is the image of a unique input, and it's not surjective since every element in the codomain is not an output. And that's really it for this question.